Hey guys, welcome back to the Blimp video channel. My name is Craig Enders and I really appreciate you tuning in. In this video, I'm going to talk about fitting multi-level models in Blimp. I'll explain how the factored regression specification extends to multi-level data, and I'll illustrate how to specify some common modeling features in Blimp. Before we get started, I want to acknowledge the Institute of Educational Sciences and point you to the project's webpage. You can download Blimp at the same homepage. To provide a context, consider an educational intervention targeting math achievement scores. Student achievement is measured on 7 occasions throughout the school year, with repeated measurements at level 1 nested within students at level 2. The random intercept regression model features 2 predictors, time-specific self-efficacy scores, and a student-level dummy variable coding the experimental conditions. Self-efficacy scores are centered within clusters such that the deviations represent pure within-student variation. In the spaghetti plot to the right, the student-level regressions differ with respect to their mean levels, or random intercepts, but the slopes are identical. In the equation, the B0J term is the random intercept residual that determines the vertical elevation of the regression lines. I represent this term with a black dot in the path diagram. I described the Blimp scripting language in a previous video, so I want to focus on the parts that are new to multi-level models. The Blimp script looks like this. To start, the cluster ID command lists the index variable that identifies level 2 units. In this example, repeated measurements are nested in student, so a variable named student identifies the level 2 units. Invoking the cluster ID command automatically induces the random intercept, so we don't need to specify that part of our model. In a multi-level model, you can center variables at either the grand mean or at the level 2 cluster means. In this example, the center command specifies that efficacy scores are group means centered around each student's efficacy average. Note that Blimp models the cluster level averages as a level 2 latent variable. That is, the centering procedure uses latent group means. Finally, the model command is identical to a single level regression model, with the outcome to the left of a tilde and the predictors to the right. Blimp figures out what level each variable is at, so there's no need to provide these details. In an earlier video, I described Blimp's default factorization for incomplete predictor variables. I want to take you through what this looks like in a multi-level model. To refresh, the specification consists of a univariate model for the outcome variable and a multivariate distribution for the predictors. Blimp doesn't make any assumptions about the joint distribution of the analysis variables. Instead, it works with the 2 simpler models and their corresponding distributions. A key idea behind Blimp's default specification for multi-level models is that level 1 predictors like self-efficacy can be partitioned into uncorrelated within and between cluster parts. The within cluster deviation scores capture differences between the level 1 scores and their latent group mean, and the between cluster deviations capture differences between the latent group means and the grand mean. Both of these components are modeled as normally distributed variables. To illustrate this partitioning, let's take a look at the self-efficacy scores for 3 students. The graph on the left shows the total variation in the efficacy scores. As you can see, the scores vary across time on the horizontal axis, and students also differ in their average levels of efficacy along the vertical axis. The middle graph shows the student-specific averages as flat horizontal lines. Again, Blimp models these means using level 2 latent variables. Finally, the graph on the right removes the average levels of efficacy from the predictor, resulting in pure within-cluster deviations with no mean differences. More formally, Blimp expresses the multivariate distribution of the predictors as distinct normal distributions at level 1 and level 2. In this example, the level 1 predictor model consists of a normal distribution for the within-cluster or latent group means centered deviation scores. In other videos, I explained that Blimp uses latent response variables to model categorical predictors. In this example, the level 2 dummy code is linked to a level 2 latent response variable, and it is this latent response variable that correlates with the latent group means in the level 2 normal distribution. Now that we've looked under the hood of the predictor distributions, let's take a step back and look at a path diagram that depicts Blimp's default specification. Looking at the left side of the path diagram, the ovals represent the efficacy latent group means and the latent response scores. These normally distributed latent variables correlate at level 2. A link function connects the latent response scores to a binary dummy code. Finally, it is this binary variable and the latent group mean centered efficacy scores that predict the outcome. In previous videos, I explained that complete predictors don't require a model because there are no missing values to impute. In most cases, it's best to simplify estimation by telling Blimp not to estimate an imputation model for complete predictors. Looking at the code on the left, I do this by listing the complete binary variable after the fixed command. Doing so links the binary predictor to the level 2 latent group means with a regression equation, and the dummy code no longer has an underlying latent response distribution. Now let's expand the example. We just saw that the latent group means are natural byproducts of Blimp's MCMC estimation. Essentially, these group means are latent variables to be imputed at each iteration of the MCMC process. We can readily incorporate these latent group means into the focal regression model. We could do this, for example, if we wanted to estimate the experimental effect while controlling for self-efficacy, or if we wanted to estimate a contextual effect where self-efficacy had distinct regression coefficients at level 1 and level 2. The regression equation and path diagram look like this. The model now has distinct regression slopes for the within student and between student parts of self-efficacy. Looking at Blimp's default factored regression specification, the focal regression model now includes an additional predictor, but the predictor distributions themselves don't change. In the syntax on the left, I reference the latent group means in the model command by attaching a .mean suffix to the level 1 predictor's name. Although it isn't necessary, I center the latent group means at their grand mean in order to obtain an intercept coefficient that represents the control group average. An earlier video walked you through Blimp output tables and described how to use the posterior summaries to answer our research questions. I want to highlight the new parts of the output that are specific to multi-level models. First, the coefficient table doesn't change with multi-level data. You may recall that Blimp reports standardized coefficients or beta weights, and it also does so for multi-level model slopes. Group mean centered level 1 variables are standardized using within cluster standard deviations. Grand mean centered level 1 variables are standardized using the total standard deviations, and level 2 variables are standardized using between cluster standard deviations. The variance section now expands to include both within cluster residual variance as well as between cluster or random intercept residual variance. For multi-level models, Blimp reports R-square statistics using expressions from a 2019 paper by Jason Reitz and Sonia Sturba. The R-square table now includes an entry for the level 2 random intercepts. The random intercept variation from the earlier table corresponds to about 39% of the total variation in math scores. Now let's expand the example by specifying a random coefficient model where the effect of within cluster centered self-efficacy varies across students at level 2. The regression equation and the path diagram look like this. Looking at the spaghetti plot in the lower right, each student now has a unique self-efficacy slope. In the equation, the lowercase b1j is a cluster level residual capturing the difference between a student's specific slope and beta 1, which is the average slope. In the path diagram, the black dot on self-efficacy's directed arrow represents the random coefficient. Now let's take a look at Blimp's default specification for the random coefficient model. The focal regression now includes a random slope for the within cluster predictor, but the predictor distributions themselves don't change. Looking at the syntax on the left, I reference the random slope by listing the level 1 predictor to the right of a vertical pipe on the model command. In random coefficient models, the distribution of missing efficacy scores is a complex heteroscedastic normal distribution that depends on the parameters of both models. The factored regression specification allows Blimp to preserve this complicated distribution without introducing bias-inducing assumptions that are incompatible with the multivariate distribution of the data. With random coefficients, the variance section of the output table now expands to include a summary for the random intercept variance, the random slope variance, and the covariance between the random intercepts and slopes. The R-square table also expands to include an entry for the random slope variation. The previous random slope variation accounts for about 2% of the total variation in math scores. As a final example, let's expand the model to include a cross-level interaction where the within-student effect of self-efficacy differs by experimental condition at level 2. The factored regression specification readily accommodates a variety of interaction effects in multi-level models. The regression equation and path diagram look like this. The diagram depicts the interaction with a directed arrow pointing from the condition rectangle to self-efficacy's random slope, which again is shown as the black dot on the straight arrow. In another video, I explained that product terms are not independent variables in the analysis. Rather, they are mathematical functions, or essentially equations within equations that depend on the lower order terms, either of which could be incomplete. Let's look at the path diagram that depicts Blimp's default specification for the cross-level interaction. The focal regression model now includes a cross-level interaction, but the predictor distributions themselves don't change. Looking at the syntax on the left, I reference the interaction by joining two variables with an asterisk on the model line. To reiterate, the distribution of missing self-efficacy scores is a complicated heteroscedastic normal distribution that depends on the parameters of multiple models. The factored regression specification allows Blimp to preserve this complicated distribution without introducing bias-inducing assumptions that are incompatible with the data. The coefficient section of the output now expands to include the product term. Although the positive interaction slope suggests that the effect of self-efficacy is stronger in the experimental condition, we would not declare the difference significant because the 95% credible interval contains 0. With most interaction effects, you can use the simple command to compute conditional effects or simple slopes. In this example, I request the self-efficacy slope at each level of condition by listing the moderator to the right of the vertical pipe. The simple command produces an additional table of output that summarizes the simple slopes at predetermined levels of the moderator. The moderator values can also be user-specified. That concludes the brief tour of multi-level modeling in Blimp. The video only scratches the surface of what's possible with multi-level models. For example, Blimp's estimation architecture also accommodates 3-level models, mixtures of discrete and continuous variables, path and latent variable models, and models with heterogeneous within-cluster variation. A detailed user guide with numerous other examples is available by choosing the Help option from the Help pull-down menu in Blimp Studio. Thanks again for tuning in, and I hope you check out future videos.